Here's problem 12.9. A uniform ladder 15 feet long is leaning against a frictionless wall at an angle of 53 degrees above the horizontal. The weight of the ladder is 30 pounds. A 75-pound boy climbs 6 feet up on the ladder. What is the magnitude of the friction force exerted on the ladder by the floor? So if we were to draw this situation, here's the ladder resting against the wall. And the wall is frictionless, so we only have the normal force. It's called P of the wall pushing on. There's no transverse force because it's frictionless. We know that this angle is 53 degrees. And we know that the ladder itself weighs 30 pounds. And that's acting at the center mass of the ladder. The ladder itself is 15 feet long. There's a boy that's 6 feet up on the ladder, and the boy weighs 75 pounds. So there's another force here of 75 pounds coming down like this. And at the pivot here where it's contact with the ground, there's going to be some kind of vertical and horizontal component to that reaction force. We don't know what those are, but we're going to represent them by V and H. So this is our free body diagram of this ladder. We don't know V, we don't know H, we don't know P. But if we choose the pivot point, contact with the ground, as our A, then we can eliminate two of these forces from torque consideration because their lines of action go through that point. In other words, V and H would be eliminated. So we need to find the moment arms for the other forces. As we look at the boy is 6 feet up at an angle of 53 degrees. So the moment arm for the boy is going to be this distance right here, and that distance is going to be, it's called D1. It's going to be equal to 6 feet times the cosine of 53 degrees, and that's going to be equal to 3.61 feet. That's the moment arm for the boy's position about point A. And then if we look at the weight of the ladder, that's halfway up, and that's going to be equal to 7.5 feet cosine 53 degrees, and that's going to be equal to 4.51 feet. That's the moment arm for the weight of the ladder. And then we have position P, which is this distance away, let's call it D3, away from the pivot point. And D3 is going to equal the whole distance of the ladder, 15 feet, times the sine of 53 degrees. And what is that? That's going to be equal to 11.98, or we'll say 12.0 feet. So if I were to make a torque diagram of what's going on here, we would have force P at 12 feet away, trying to make this thing rotate counterclockwise, which would be indeed a positive torque. And then I would have two other forces. I would have 30 pounds with a moment arm of 4.51 feet, trying to make this thing rotate clockwise, which would be a negative torque. And then I have the 75 pounds with a moment arm of 3.61 feet. And this is also trying to make this rotate clockwise where it has a negative torque about point A. All the torques cancel out, and we have a net torque of 0. So the net torque about point A is 0. That's equal to 12 times P minus 4.51 times 30 pounds minus 3.61 times 75 pounds. We can solve this for P. P is going to equal 4.51 times 30 plus 3.61 times 75. All this, divide by 12. So that is 33.8 pounds. Nice to know. That is the force P, normal pushing on the ladder from the frictionless wall. But we want to find H. We want to find the transverse force of the floor on the ladder, which would be the friction of the floor on the ladder. Well, we realize that the summation of the forces in the x direction should be 0. In this case, that's going to be equal to H minus P, because that's all we have as far as forces in the x direction. So H is actually going to be equal to P, and that's going to be equal to, at least in magnitude, 33.8 pounds. So the frictional force of the floor on the ladder, which is our force H, is 33.8 pounds, and that is our answer for this problem.